So we are going to discuss about the accept reject algorithm. All right. So the statement of the accept reject method is let fx be a PDF of the random variable x, and suppose that y is a random variable with PDF fy. Okay. PDF GY. Here fx is called the targeted PDF and GY is called the instrumental or proposal PDF, and use a random variable with uniform distribution between 0 to 1, where y and u are independent for some constant m. So basically what is the concept of the accept reject method is, if you have any random variable, okay, if you have any random variable x that follows any distribution fx, all right, and you want to generate the random number from the PDF fx for random your given random variable x, all right. So for that one we studied one method, that was inverse CDF method, right? So what we were doing in the inverse CDF method, we were writing if x follows the distribution function fx and with CDF fx, and if we can write it as x equals to f inverse u. So whatever the and u follows the uniform distribution with 0 and 1. So at that time, whatever the x we will generate from this function, it will follows the same PDF fx, right? But if we are not able to do that, or the PDF or the CDF in the so complex form, so how we will generate? So at that time, what we do, we just assume another density function, or we find out another density function g. All right, we need to find out one more density function gy that should overlap, your fx in terms of the graphical representation in terms of PDF, right? If you just see like this, if you this is your, suppose gamma function, you have gamma density function, fx is your gamma density function. Okay, fx is your gamma density function with parameter a and b. So if you have the density plot of x will be like this for the gamma, right? So we need to find out some other distribution that should overlap this density function completely. Okay, so we are saying that suppose we have g that is going to overlap that one with the condition fx should be less than equals to mgy. Means even if gy is not going to completely overlap this one, it is not necessary that for every single point of x the density of gy or g dot will overlap it. Yes or no? If I am having the gamma density function like this, and I am finding some my proposal density or instrumental density, and it is like this. It is overlapping in the beginning, but later it is not covering it properly. Right? From here to here, they are equal, and after that, it is going below, so it is not going to overlap it. Yes or no? It may possible when you have the density function. Yes or no? Right. So that's why we are going to multiply by some constant m in G in such a way that it should overlap it completely like this. Okay, so m is a constant that we are going to multiply in such a way that it should overlap completely like this. Okay, if this is my density fx, this lower line, lower plot is my density of fx, and the above one the above line that's showing the plot of m into gx. All right. So whatever the sample, basically what this graph is showing, that whatever the sample that I'm going to generate from y, all right, so in that one, whatever the values I'm going to generate from this variable, whatever the values I'm going to get from this distribution, I'm saying that it is y, the observation that I'm going to generate from the g dot, that is y. So y, I will put it equals to x. If it is, it will lie in this area or under this area. If it is going to lie above this one, I will reject those values of y. I will accept only those values of y that will lie under this plot or this line. All right. So for that one, what is the theorem that I have? It says that I am going to generate the y from gy, all right, from my targeted density function. Sorry, from my proposal density function, and u I am going to generate from the uniform distribution. So after that, I am going to put the condition is that u should be less than equals to fx divided by m into gx. All right. Then if this condition is going to be satisfied, so at that time I will assume that x is equals to y. Otherwise, it is not equals to that one and it is lying in this rejection region. The y that I am generating, that is lying in this rejection region. So that's why I need to go back again to step 1 and I need to generate again y from the gy and u from the uniform distribution, and again I need to compare this one. All right, here what you are going to do basically in fxy, that you have fx divided by mgx, here it is basically fy divided by mgy. That value that you are going to generate from the y, you will keep here, and then you are going to find out the ratio between both of them. All right, it should be greater than equals to u, uniform distribution, right? In that condition, if this condition is going to be fulfilled, so whatever the values of x that you are going to generate, this one x equals to y, you will say that that has the PDF of fx. All right. So after that, how we are going to validate this one? So we had the proof of this algorithm. In that one, what we are saying that we need to find out the CDF of probability of x equals less than equals to x, that we need to find out. All right. What it is basically, we are writing it as the probability of y is less than equals to x, given that u less than equals to fy divided by mgy. Why I am writing this one? The key idea or the basic idea of that one, we are going to keep x equals to y when if y is accepted. Right? Means if you just see here, what we are saying? We are saying that in the third step, we will accept y is equals to x, whatever the value I am going to generate from the y, I will keep it equals to x, or I will assume it my x random number if it is going to fulfill this condition. Right? So when this condition is going to be fulfilled, so my x will be equals to y. So that's why I am going to replace my x less than equals to x with the y less than equals to x. Right? Because my x is basically equals to y. My x, whatever the x in the last I am going to assume or I am going to accept, that is basically y from the gy. Yes or no? Are you getting this point? First I am generating the value from the y, I am going to generate from the gy, and after that I am going to check this condition u less than equals to fy divided by mgy. Right? This condition, if it is going to be fulfilled at that time, I will accept whatever the y I am going to generate, y1, y2, yn. So yi I will accept if it is going to satisfy this condition. Correct? So that's why I am going to replace x less than equals to x with probability y less than equals to x, given that sample y is accepted. What is the meaning of that one? Given term. It means that the sample is accepted. Okay. So here, so we basically defining it as the x is basically equals to y, given that u is less than equals to fy divided by m gy, that is basically means accepted. Sorry, y is accepted. Whatever the random number I generated, that is accepted. That is the meaning of this term. All right. So that is basically probability x is equals to less than equals to x, this one, till x less than equals to x is basically probability y less than equals to x, condition that y is accepted. All right. So that's how we wrote this term here. Right. Now come again to the next line in the proof. So when the conditional probability is given, so how you will write it? So probability A given B is equals to probability of A intersection B divided by probability of B, right? So from this formula, we wrote this one, probability y less than equals to x intersection u less than equals to fy divided by m gy divided by probability of u should be less than equals to fy divided by m into gy, right? Is there any confusion in this one till here in the first two steps? Do you have any confusion in first two steps of the proof? Right. So now come here in this part of the integration. So if you just see here, y less than equals to x intersection u less than equals to fy divided by mgy, what is it? This is the joint probability of two random variables, because u is a random variable, right? U is a random variable that follows the uniform distribution, and y is also a random variable that follows the gy, right? So you need to solve the integral for both of them. Correct. So first of all, you need to solve this integral because you have the y here. Y is involved in this integral. Right. What is the meaning of this one? It's basically, if you are going to consider this one in the form of this is basically like this. On the y x-axis or the horizontal axis, you have the y, the observation fixed value of y you are assuming here. In that one, uniform distribution, you are going to solve it for the fixed value of y. Correct? You will generate the one value of y from gy and you will put in this expression fy upon mgy. So for fixed value of y, you are going to solve this one, this integral. Yes or no? Here you are going to fix y or not? Tell me. Yes or no? Nobody is speaking. Are you getting this point? Yes or no? Tell me. You are not getting. Basically, see, what I am going to do it in the acceptance rejection method, I have my x that I am following fx, that is unknown. X is unknown here, means I need to generate the values of x1, x2, xn. Right? I want to generate the random sample from my given PDF. My PDF is in a very complex form. Right? My PDF is in a very complex form. So the CDF also. Right? So at that time, I cannot imply the inverse CDF method or importance sampling method. Right? So what I will do? I will plot my density function. I can draw my density function. Yes or no? For the given values of the parameters. Right? I find out that this my density function is look like this. Okay. My density function is look like this. The graph of my density function. Now I need the values of x that will also follow same type of plot, right? So how will I get these values? So at that time, I will find out one another distribution. Okay, I need to find out one more distribution. The shape of that distribution should be look like the same of my fx. I need to find out that distribution, right? In that one, it is not necessarily every single time that it will cover it completely. It should overlap my fx completely. It is not possible. Sometimes it will overlap or sometimes it will not, right? So at that time, I am going to introduce a constant m by in such a way that after multiplying by that constant in gx, it will overlap my fx completely, right? So at that time, I will get the y. I can generate the y from gy that I am my proposal distribution that I am finding. That should overlap. When I am going to generate the values of gy, the all well tell me one thing, the all values of gy will overlap my fx. If I am going to generate the values of y from gy, will it overlap all the values or all the values will lie here only? What will happen? If I am going to generate the values, this is my distribution. Oh, sorry. This is my distribution, right? This is my distribution. So if I'm going to, and I am having one density function. This is my gy or m into gy, you can say, and this is my fx. So whatever the values I will generate from the gy, all the values will lie here only, or it will lie here. It may lie here also. So if it is going to lie in this region, I need to remove all those samples. I need to remove all those values that will lie in this area. Yes or no? How will I remove them? I will remove them by this comparison. I will generate the values. Okay. I will generate the values from the uniform distribution, and whatever the values of from the uniform distribution I am getting, if that is less than equals to my fx divided by mgx, means whatever the values I am going to I will generate one value u1 from the uniform distribution, and I will compare this with my one value that I am going to generate from gy. I will put that value, say y1 here, and m into gy1 here. So whatever the ratio I will get, if it is greater than this uniform value, I will accept it, otherwise I will reject it. So means if this ratio is less than equals to, if this ratio is greater than equals to u1 for the value y1, I will accept y1 and I will keep y1 equals to my x. Otherwise, I will remove it and again I will check and I will put the again another value y2. Okay, with m into gy2, I will check again this one u2, right? If it is again greater than, this ratio is greater than u2, I will accept this as x. If it is not, then I will not keep it and again I will go back to the first step, again I will generate the value, right? So that is the basically procedure. Are you getting this procedure? Are you getting this one? So what we are going to do that? So in this one, what I was saying that, so you didn't have the problem up to here in first two steps of the proof, right? So now coming back here, so here my u, there is a condition on u. I have the condition on u, right? U should be less than equals to, u should be less than equals to fy divided by mgy, right? Means my u is depends on y that I am going to generate from the y, right? And u is depends on the all values of y, not the selected one, right? Because I need to check the condition for every single value of y. Yes or no? So whenever I'm going to check the condition, I'm going to generate the this condition, this generate value y I'm going to generate. So this is the single value, na? Y2 is a single value or not? Here, when I'm going to check this condition, y is a single value or not? Y2 is a single value only, right? So that's why I am saying that on the y-axis or the horizontal axis, y will be there, and on the your y-axis or the vertical axis, u will be there. All right. So you need to find out the this probability that is coming under this region. That will come under this region. All right. So we need to compute 0 up to, because it is lying between 0 to 1, so it will be 0 to fy divided by mgy. That's why we are writing this integral here, because we are checking on each and every single value of y, right? So that's why first we will integrate over the range of this one, then we need to integrate over the range of 0 y, that is 0 to minus infinity to minus infinity to x into with the density gy, the density of y, that is gy. So that's why we are writing dy, right? After that, in the denominator, what is there? We are integrating over the range of minus infinity to infinity for gy dy, for the gy density. Why we are writing over the range of minus infinity to infinity here? Because again here in the u we have the y. Y is involved here. Yes or no? So you need to check the probability at each value of y. So that's why we are integrating over the range of minus infinity to infinity here with respect to the density gy. So when you are going to integrate it, and u is, what is the integration of this one? Integration 0 to fy divided by mgy. Say it equals to t. That follows the uniform distribution. What is the density of the uniform distribution over the range 0 to 1? What is the density of uniform distribution? Right. 1 upon b minus a, that is your 1 upon b is 1, a is 0, so that is equals to 1. So that's why integrate 0 to fy divided by m into gy 1 du. So what is the integration of this one? That will be fy divided by m gy minus 0. Right. So that's why you have the fy divided by the mgy. So mgy will cancel out here. Fy divided by mgy, and gy was there in the multiplication in the numerator. So gy will cancel out. And again, when you will do the integration in the denominator, so again it will be fy divided by the m into gy into gy. So gy will again cancel out here, and m will cancel out again here from the numerator and denominator, right? So what you will have here? Remaining things. That is basically integration minus infinity to x fy dy divided by minus infinity to infinity fy dy. So the integration over the range of random variable of PDF, that is equals to 1, right? So it is equals to 1. So, and what is it? It will be integral minus infinity to x fy dy, that is probability y less than equals to x, that is your CDF of x. So means when you will generate the random variables, random values from y of y from gy, and then u from uniform between 0 to 1, and when you will compare this one, this condition u should be less than equals to fy divided by m gy. If this condition holds, so your x is basically equals to y, and x follows fx. So that is your acceptance rejection method. And the limitation of this method is that, or the critical point to find out the gy, that should overlap always your fx. All right. So for that one, we check the one code we checked earlier. All right. Sorry. So here, what we are doing, is it visible for you? The R code. Is it visible? All right. So what we are going to do, we are going to remove all the previous object here. Then I am going to plot the density function. I have two density function here. All right. First density function is the square root of 2 pi divided by the e raised to the power 1 into 1 upon pi into 1 plus x raised to the power 2 raised to the power minus 1. That is my one density. All right. This is my one density function. And after that, 1 upon square root of 2 pi into e raised to the power minus x square by 2. That is my second density function. That is basically standard normal distribution. Right. So I'm going to check them whether they are going to cover each other or not properly. All right. So if you just see that fx is going to be covered in the blue one, is my standard normal distribution, and the red one is my another density function, right? So my another density function is completely overlapping my standard normal distribution, right? So here, after that, I am introducing a null vector here to store the values of x, whatever I am going to generate. And after that, what I am going to do, I am introducing a val I as 0. After that, I am introducing here repeat and break command. Do you know why we use the repeat and break? Do you have any idea for the repeat and break command? Repeat and break is basically how we use the for loop. Can you tell me how we use the for loop? We have the condition and how many times we are going to repeat that condition. For that one, we have the for loop, right? And while loop, we have the condition. Till the condition is not going to be fulfilled, the loop should repeat. For that one, while loop is there, right? Here, what is the repeat and break is that? Repeat and break is that I have the condition. If condition is satisfied, is going to be satisfied, it should run. If condition is not going to be fulfilled, so it should break the loop and again it should go in the beginning and again it should start from the beginning. All right, means I have the number of conditions in that one. What are the conditions I am having here? I have three steps here, right? First, y should generated from the gy, that is my first condition. Second thing is that you should generate from the uniform distribution. That is my second condition, right? After that, I am saying that u should be less than equals to fx divided by m into gx. That is my third condition, right? If any of these three condition is going to be break, so again it should go start from the beginning, right? Basically, we have only one condition that should be tested here. Y is going to definitely we are going to generate from the gy, so that is not going to be contradict, right? Or you will also generate from the uniform, that is there is no complexation there, right? No complexity, but this condition we need to satisfy. So if this condition is not going to satisfy, it should go again and it should generate, the code should generate the y from the gy again and u from the uniform, and again it needs to check if this condition is going to be fulfilled. I will keep the values of x, otherwise it should go again in the initial stage and it should generate the values of y from the gy and u from the uniform. So what we are going to do here in this code, we are saying that I'm going to generate u from the uniform distribution. Okay, one value at a once from between 0 to 1, and y I am going to generate from the tan. Okay, tan is your tan theta from your trigonometry pi into u naught minus 0.5 and f naught. Okay, basically I'm going to generate the y from the this condition. After that, what I'm going to do, I'm going to generate the f naught from the square root of pi by 2 expression of e raised to the power minus y square by 2. Means whatever the y I'm going to generate, that should I'm going to put in this formula, in this my standard normal variate. After that, I'm going to decide here my m. Okay, you need to decide your m very carefully, and sometimes how we define the m, give me a second. Yes, so there is a one more method to define the m. What we do basically, is it visible for you? we will optimize. We use the optimize command here. Okay, because that it should be the maximum difference. M is basically the maximum difference. So F1 that should lies between 0 to 1. That should not be greater than 1, and maximize equals to T. All right, that is the command $sign objective. This is the command to find out the M. Okay, whatever the F is your there, whatever the density F1 you have, so for in that one you will use the optimize command and you will find out F1 for optimize the F1 with respect to between 0 to 1 for maximum T. All right. Sorry, maximum is T is basically maximum is true. Okay, maximum T is basically maximum is true, and that is your command that we use when we don't know the values of the M. Okay, that's how we define the values of M here. Because M should be lies between 0 to 1. It should not be greater than 1. Okay, so in that manner, but here I am defining my M, that is square root of 2 into pi divided by e raised to the power 1. After that, I am going to check this condition. If u is less than equals to f naught divided by m or not. If this is going to be satisfied, I will take yi equals to my y, whatever the y I am taking, that should store in v other, and I should be equals to I plus 1, because I am going to generate how many values I am going to generate here. I am going to generate 100 values. All right. So otherwise, if this condition is not going to be fulfilled, this condition is not going to be fulfilled, it should break and again start to generate the random values. Okay. And again, I will put in the f naught the values of y, and I will find out the my m again, and then again I will compare this one and I will run it number of times till my 100 observations of v is not going to be completed. Right. So that's how I am having the my 100 random numbers from the standard normal distribution. If you just see here, this is the similar to the your blue graph, blue plot. Both are quite similar, and they have the -4 to 4, and this is lies between -2 to 2. And if you just see here, you have the maximum observations are between -2 to 2 only. So means you are getting the accurate values from your acceptance rejection method. Right. Here, what I am going to do, here I had the another density function. All right. And what I am going to do here, I am going to generate my G from the generalized beta distribution of second kind. Right now, this package GB2 is not working in my laptop. Otherwise, you can check it in your, and we are going to use the same method here. Okay. Same procedure we are having here, but instead of putting the some values of y m, we are changing m every single time by the optimize of f1. That is the difference between these two commands, right? So that was your acceptance rejection method. Do you have any doubt? You can ask me right now. Do you have any doubt in this one? Are you getting this one completely? You just try it once for the gamma distribution. Okay, what you do, you just try it. You suppose that how you will do in that one. You just suppose that your x follows the gamma distribution with parameter a and b. In compared to that, consider the y that follows the Weibull distribution. Okay, that follows the Weibull distribution with parameter lambda and k. Right, and then apply the acceptance reaction method. All right. You people try it. Okay. X follows the gamma with parameter A and B, right? And variable follows the Y follows the variable distribution with parameter lambda and K. You can take the value of A and B and lambda and K from your side. Whatever the values you want to take, you can take the values of A and B and lambda and K and try the acceptance rejection method, right? Yes, tell. Um, while loop, because see, thing is that in the while loop, problem when you use the while loop, what is the condition for the while loop basically? While loop you use till the condition is not going to be satisfied. This loop should run continuously, right? Here, what I means in that one, it can go up to the infinite number of times, right? But here, what I am having in the repeat and break is like that. If you just see repeat is going to start from here, what should it repeat in the repeat? You should repeat the uniform U. You need to repeat every single time. Y you need to repeat. F naught, value of F naught you need to repeat. And you need to repeat the M. After that, what you need to do? There are the if else condition. Okay. You need to check this condition. After that, what you need to check here till how long it should run your repeat and break loop till the length of V is not equals to 100. Okay. If you are going to apply the while loop, what is the condition you will put here? Same thing you can do, right? But the benefit of that one, in that one, it will be little bit confusing while when you are going to use the while loop. You can use the while loop also. That is not a problematic, but at the time you have to be very conscious because your single means less than or equals to sign can take you up to the infinite to the up to the infinite loop. All right. But here, what is the thing is that all the things are very simple, right? What you need to give here, the length V should be equals to 100. You need the 100 numbers. If you just put here 1000, that is your command. If you want to change it, but in that one, in the while loop, you need to change it every single time. So when you will apply for that one, what if we say that X and Y, you can apply, you try it in the while loop also. All right, you try it in the while loop also. Right. If you just see here in the second one, I think in the second one, see the same problem you will face here. What the problem I am facing here? I am using the for loop. Okay. I am using the for loop. I am generating Y from the generalized beta distribution of second kind. I am generating U from the uniform distribution. Right. After that, I am checking this condition, that is Ui should be less than Fyi divided by Mji. Right. J is basically my proposal density. If this condition is going to be fulfilled, Xi equals to Yi. If this condition is not going to be fulfilled, what should happen? What I will do? I don't have this condition here. But in the repeat and break, I am having that one. So if this condition at that time, my sample size will compromised in this for loop. In this for loop, my sample size will compromised. That is the problem. Okay. But in the repeat and break, what is there? My sample size will not compromised at all. Because it will check the condition. If this condition is not going to be fulfilled, it should go back and it should start from the beginning again. Okay, that is the basically difference between while, repeat break, and for loop. Okay, are you getting my point? What I am trying to say, right? So that is your that one. What we say, accept reject method. So after that we discussed that one. What we call it, Metropolis algorithm. All right. So what was the Metropolis? So if you just see here in the acceptance rejection, you need a one density that should completely overlap your density under the study, right? That was the case in the acceptance rejection method, yes or no? But here in the Metropolis Hastings algorithm, what is that? So in that one, Metropolis Metropolis algorithm uses a method that is similar to the accept rejection algorithm. Suppose our goal is to draw the samples from the sum distribution p theta. Okay. Earlier we were saying that our x is following the fx. Now I'm saying that my theta follows the p theta that I want to find out, where I can write down my theta my p theta I can write down in the form of f theta divided by k. I can approximate my p theta equals to f theta divided by k, where k is my normalizing constant. Okay, k is any constant term. Here, if I can write like this, my density function of theta. So one of the advantage of using the Metropolis algorithm is that the normalizing constant is not need to be known. Okay, why we are saying that it is not need to be known? Okay, just remember we don't need to remember we don't need to know this value, the values of the k here. Why it is? In practice, when we compute the posterior distribution of in the Bayesian method, it is very complicated to obtaining the normalizing constant integral fx given theta into g theta of d theta. The Metropolis algorithm. So here, what we are going to do? Okay, how this method is going to work here? It is basically, if I am saying that my theta follows the p theta, all right, and I can approximate it by f theta divided by k. I can approximate it by theta k. So what I need to do in the Metropolis algorithm, I need to generate a value of theta. Oh, sorry, I not need to generate. I just give the one values of theta, that is theta naught. I will say it as the initial value. Okay, I am independent to give the value theta naught here, but I just need to be careful that whatever the values of theta naught I am going to provide here, that should lies theta naught should lies the range of theta. Okay, that should lies in the range of theta. It should not go beyond the theta. Means if my theta is lies between 0 to infinity, so my theta naught, whatever the values of theta naught I am going to provide, that should also belongs to 0 to infinity. It should not be minus infinity to infinity. All right. I cannot provide the negative value. That I need to be very careful. After, okay, so start with any initial values of theta naught which satisfy f theta naught greater than 0. Right. So means I was approximating my p theta, my density, with f theta divided by k. Are you getting this point? Yes or no? See, what I'm going to do here. understand in this way. My x follows fx distribution, right? I am not able to generate the values from fx, my values of x1, x2, xn, these values I am not able to generate directly from fx. Okay, so what I will do, I am saying that my fx, I can approximate it, my density of fx, this density, I can approximate it in the form of gx divided by k. If I can approximate where k is any constant, are you getting up to here? My x follows the density function fx, right? I cannot compute the sample or random sample x1, x2, xn directly from my fx. So at that time I can approximate, if I can approximate my fx in the form of gx divided by k, in this form I can approximate. So what I will do, I will start with some initial values of x naught. Okay, I will give some initial value here from my side. Listen, see here. Okay, I will start with some initial value. After that, what I will do, here two things are there. X naught, whatever the value I am going to give x naught, that should satisfy the range of x, first of all. Second thing is that while I am going to put this x naught value in G, here it should be greater than 0, right? It should not be Gx naught should be less than equals to 0. Okay. It should not be less than equals to 0. It should be always greater than 0. These two conditions should be satisfied. First condition, x naught should belongs to the range of x. Okay. It should belongs to the range of x. Second thing is that gx naught should be greater than 0. These two conditions should be satisfied here. Right. After that, what I will do, I will use the current value of theta. Okay, sample is a candidate of theta star from some jumping distribution q theta 1 comma theta 2, which is the probability of returning a value of theta 2 given a previous values of theta 1. This distribution is also referred to as a proposal distribution. The only restriction on this density in Metropolis algorithm is that it is symmetric, right? So means I will generate the values of theta naught. Okay, after putting the values of theta naught, I will put this value, whatever the values I am going to generate here, I will put it in some symmetric distribution. I will introduce one symmetric distribution here, Q1. For that one, theta 1, theta 2 should be equals to Q1, theta 2, theta 1. I need to introduce one values, and for the given a candidate value theta star, calculate the ratio of density at the candidate theta star and the current value of theta, say theta t minus 1. So I need to, basically what I need to do, I will introduce x naught here. Okay, I will start with the x naught. With the help of x naught, I will put start. I will generate the one value from this density function that should be symmetric. Okay, and I will put it here and I will compare it with the previous value that I generated, that is p theta t minus 1. What it was, basically p theta 1 was f theta star divided by k f theta t minus 1 divided by k. Alright, so k will be cancelled out. So that's why we don't need to know the value of k here because k will cancel out. How it will work? If I just show you with the example, uh, if you just remember this example from the previous lecture, is it visible for you? Right. So, give me a second. All right. So, what I'm going to do, what is the meaning of this one? I have a one distribution here that is named as generalized Lindley distribution. Okay, forget this one. Okay, I have the generalized Lindley distribution here. And this is the mean of generalized Lindley distribution, that is 1 upon 1 plus theta into alpha plus beta divided by theta. Here A is defining alpha, B is defining beta, T is defining theta, N is my random number that I want to generate. Okay, are you getting this point till here? And here I am introducing Ez as a term, that is 1 upon 1 plus theta into alpha plus 1 divided by theta plus beta into beta plus 1 divided by theta square. When I am going to subtract mu square from here, that is basically your expected value of x square. This is your expected value of x square. Okay. So what is the formula of variance? Expected value of x square minus expected value of x whole square. This is the formula of variance, right? So what I am going to do? Expected value of x square minus mu whole square, right? So I am getting the variance. So after that, in the HD square root of the variance, that is my standard deviation, correct? After that, I am introducing a null vector here in the terms of numeric. So because it is continuous, so that's why I am introducing numeric of the size n, that is 5000 sample that I am generating. Okay, so this is the null vector right now. After that, in f, what I am going to do here, this is my density function of generalized Lindley distribution, that is e raised to the power minus theta z. Z is my random variable. Okay, divided by 1 upon theta raised to the power alpha plus 1 into z raised to the power alpha minus 1 divided by gamma alpha plus theta raised to the power b into z raised to the power b minus 1 gamma b. Right, this is my density function. Okay, if you are, give me a second. I just show you where it is. Oh, sorry. Mm, right. So this is the density function basically that we have. We are considering here, this is the density function 1 upon 1 plus theta into e raised to the power minus theta z, theta raised to the power mu plus 1, z raised to the power mu minus 1 divided by gamma mu plus theta raised to the power beta z raised to the power beta. This is eta basically, but I'm using the beta here. Beta minus 1 divided by gamma beta. So this is the density function that we are using. So if you just see this one, it is very difficult to generate the random number from this distribution. Yes or no? What is the CDF? If you just see the CDF here, did I write the CDF? No, I didn't write the CDF here, but this is the density that I am writing. So can you generate the random number from this density directly? It is very difficult, right? So what I'm going to do here, after that, I'm giving because my z, the random variable, if you just see here, what is the range of my z and my parameters? That is between 0 to infinity, right? This is the range of my parameters 0 to infinity, right? Positive side of the real line. So I am giving the values of z of my random variable initial guess that I am giving, that is 2.2. So that is going to fulfill the condition of the range of z 0 to infinity, right? So I am saying that my first values of z new should be whatever the value I am providing here, that is 2.2. After that, I am starting the for loop I equals to 2 to n, because I need the 5000 random variables. After that, I am going to introduce the candidate density, that is normal distribution, from the normal distribution. And what I am going to do, I am going to use the mean and standard deviation same as I had from here. Whatever I am going to compute from here, I am going to use the same mean and standard deviation to generate the random number from the normal distribution. Normal distribution is a symmetric, right? And here we are saying that the jumping distribution that we are going to generate, that should be the symmetric. So that's why we are assuming here it should be normal distribution. Okay. After that, I am introducing a one condition here from my side that is not given in the Metropolis algorithm. That is, if candidate is greater than 0, so candidate density should be equal to the candidate density. Otherwise, candidate density should equal, I will take it equals to 0. Why I am doing it? Because normal distribution can generate the random number in the terms of negative observation or not. Because what is the range of normal distribution? Minus infinity to infinity. So that's why I need to ignore the negative term, because for my distribution condition is that x or z should be greater than 0. That is the condition that I am having. Yes or no? I am having this condition only, na? My w should be greater than 0. So that's why I am saying that negative term should be ignored. After that, what I am going to do here, I need to find out the ratio of my generated value and my current value, my right. So what I'm going to do here, f candidate, the value that I'm going to generate from the normal distribution here. Here I will get one random value or not. So that random value I'm going to put here instead of z, I'm going to put in my density divided by, I'm going to put my initial guess 2.2 into my density here. I will get the ratio. Yes or no? See, what I am going to do here, for the given values of the parameter, I have mean 2.33. I have the variance 2.55, I have the standard deviation that is, I have the standard deviation that is 1.59, right? Now I'm using Z new. Z new is my null vector here with the 5000 zeros. So after that, what I'm going to do, I'm going to introduce Z note as 2.2 and I'm going to store the value here in the first, in the my vector of 5000 null vector of the 5000 of zeros. The first place it should take 2.2. If you just see here now, it will be 2.2 and others are 0. Okay, I should increase the size. Give me a second, sorry. Right. So after that, I need to generate the values from the normal distribution with the same mean and variance. So I generated this random value first time. After that, what I'm going to do, I'm going to put this value in the density function. Sorry, I didn't run the density here. So I will run this and now I can find out f. Okay, so this is my value of my density function for the generated value from the normal generated value can from the normal distribution and for the given parameter value 3, 8 and 2. Right. Similarly, I can find out my probability for Z naught. Right. So I am having the ratio of both of them. Right. Now I need to check that whether the ratio, which one is minimum here? The ratio and 1. So the ratio is minimum in compared to 1, right? After finding this ratio, I am putting it equals to alpha. I need to check that u should be less than minimum of 1 alpha. All right. And u I am going to generate from the uniform distribution. If this condition is going to hold, I will accept the random value that I generated from the normal distribution. Okay, whatever the value that can I generated, the value can that I generated from the normal distribution here. This value that I generated from the normal distribution, if this one is less than my u, I will accept this one and I will keep it in my z new. Otherwise, I will reject it. Okay, so in that one, I will check here. Sorry. So I will check here. So what is u here? U is 0.13. So 0.13 is less than 0.54 or not? Here, this is my ratio. So 0.13 is less than 0.54. So I will accept this one, this candidate value that I generated from the normal distribution. Okay. And I will repeat it 5000 times, this procedure. Okay. So what I'm going to do when I'm going to repeat this. Okay. So accept the proposed values if the uniform value is less than and minimum of 1 and alpha, else reject it and return to the step 2. Means what is your step 2 is that generate the random number from the your candidate or jumping distribution. Means again you will generate the random value here from the normal distribution and again you will compare this ratio. with uniform value. That is your Metropolis algorithm. So if you just see here, this is the density function of the Lindley distribution. Okay, generalized Lindley distribution. And what is the mu I received earlier? That was 2.33. And what is my new mean? Is 2.05. That is close to my actual mean, right? And my variance is 1.20, and here my variance is 2.55. Why it is 2.55? Because of the formula. All right. When you use the command var in that one, in the R software, there is a problem in that one. What is the formula of the variance? 1 upon n summation xi minus x bar whole square. That is the formula of the variance, right? Correct. But R takes the formula 1 upon n minus 1 summation xi goes minus x bar whole square. That is the problem in the direct command of var. The var command takes this formula. Okay. So if you want to find out the exact variance, so what you need to do here, in this formula var of x, you need to multiply by n minus 1 and divide by n. So after that, you will get the exact variance. Okay. Did you know that earlier? What? VAR. VA. This VA I defined here in the beginning, the variance of my generalized linear distribution. That is different. So I'm just talking about this one, VAR. My VAR is right now 1.20. Here it is 2.55. That is because of this formula. Okay. Now we will talk about that one, Metropolis Hastings algorithm. All right. So Metropolis Hastings, in the Metropolis Hastings algorithm, what he did, he generalized the Metropolis algorithm, and after that, what he did, he multiplied by that jumping distribution in numerator and denominator. Earlier, in the Metropolis algorithm, we were ignoring the jumping distribution that we were assuming earlier. Here, in Metropolis algorithm, when we were taking that one, what we call it, the ratio of the current value at the previous value here, so we were ignoring the density, jumping density, yes or no? We were not taking the ratio of that one also. But in the Metropolis algorithm, what is the change here? We are going to multiply by theta jumping density of theta star comma theta t minus 1 divided by q t minus 1 and theta star. All right. So that is the only difference in that one. Right. If I just check it. So what you need to do here in this code, the remaining code, the entire code will remain as it is. What you need to do here, simply you need to divide by d norm can, you will find out the density or the probability of the normal distribution by can with the same mean and the original mean and standard deviation divided by z naught comma mu comma sd. Whatever, see, basically what you are going to do here, you generated a random number that in candidate from the normal distribution with mean, mu and standard deviation. That mean and standard deviation you need to provide from your side. Okay. But because I have the mean and variance in the closed form, so that's why I am putting the same value that I'm going to get here. Otherwise, you need to provide this value mu and standard deviation from your side. Okay. Here, this mu and SD you need to provide from your side in other cases. But here I am getting the values of mu and variance in the closed form. So that's why I am providing the exact value. Otherwise, you need to provide that one. So after that, you need to find out the probability density functions value here. All right. From the for the given whatever the value you have generated. All right. Why we use the d here in the R for the density, right? So you need to when you have the value of the mean and you have the value of the standard deviation and you have the values of x, so it will provide you the density value of the density function denorm command. Yes or no? So I will find out the density. I will find out the density for my generated value as well as for my initial guess. And I will take the ratio of that, all of them also. That is the only difference here. Otherwise, the entire command will remain same as the Metropolis algorithm. All right. If you will do it, see. Now, check. Your mean is right now 2.32 and your variance is 2.64 for your generated values. What was the exact mean? What was the exact mean was 2.33. What was the variance? 2.55. Now you have the mean and variance are almost equal. Right? So Metropolis Hastings algorithm will give you more accurate random numbers in compared to Metropolis algorithm. When you are going to multiply and divide by the your jumping distribution. Right? Are you getting this point? If you just see here, this 2.32 is the mean of my generated values and 2.64 is the variance of my generated values. Here I am having the mean 2.33, that is the my exact mean from the formula, from this formula, right? And this was my exact variance from this formula. So if you will see, you will not find the significant difference between both of them, right? And if you will see, you will find the almost convergence here, right? And I will check the ACF of Z new also. ACF of Z new. Completely fine. Only initial few values, initial, you can say initial 10 values have the autocorrelation. Other than that, all are the independent, right? All other values are independent. So that is your Metropolis Hastings algorithm. All right. So now we will proceed. Do you have any doubt in this one or any question? Okay. So after that, here I just took some examples. Suppose we are interested to simulate the posterior distribution of theta, where theta is the parameter of the probability of success in the binomial distribution, that is y follows the binomial distribution and theta. And let us assume that we have the single observation of y as y equals to 3 from the binomial distribution with n equals to 5 trials. So further suppose that the posterior distribution of theta is from uniform distribution, that is g theta equals to 1. So posterior distribution will be, so what we are saying that, here we are saying that y follows the binomial distribution with parameter n and theta. Here we are saying that n is equals to 5 and y is equals to 3. So what will be my density here? So what will be my PMF? What is my PY? 5c3 into p raised to the power, that means theta raised to the power 3 into 1 minus theta raised to the power 2. Right. So this is the constant term into 1, that is my prior uniform. So my posterior density will be theta raised to the power 3, 1 minus theta whole square. So my posterior will be proportional to theta cube into 1 minus theta whole square. Right. So Metropolis algorithm to simulate the targeted density given in equation 1. So how you will use that one? So I need to find out the values of theta here. So how I will find out? I will put the values of n chan equals to 1,000. Means 1,000 times I am going to generate the values of theta. After that I am giving the y equals to 3, n equals to 5 and theta equals to repeat 0 to n chan. Means that is the null vector again. And theta 1 equals to 0.04 because theta lies between 0 to 1 because this is the probability of success, right? So after that I am applying here for loop, okay, 2 to n chan means 1,000 times. After that theta star I am going to generate from the uniform distribution 1 0 comma 1 because my jumping of the proposal density function should be uniform. I cannot take here normal distribution. Earlier I was taking in the Metropolis algorithm, I was taking here. I was taking the normal distribution, but I cannot take the normal distribution here because my observations lies between 0 to 1, right? So for that one, what I will do, and after that I will take the alpha, that is minimum of theta star raised to the power y, that is my posterior density 1 minus theta star raised to the power n minus y divided by theta I minus 1 raised to the power y into 1 minus theta I minus 1 raised to the power n minus y. So if you will put I equals to 2, so it will be 2 minus 1, so that is 1. What is your I1? That is your 0.04. So here it will use 0.04 to for the first value. It will take 0.04. All right, as the theta. After that you will take uniform, again you will generate the R from the uniform because you need to compare whether your U is less than alpha or not. If it is less than alpha, then theta I equals to theta star. Otherwise, theta I should be equals to theta I minus 1. Means it will take the previous value and again it will start from the beginning. All right. So in that one, you can generate the values. All right. This is the basically values after the first I am generating plot 1 to 1000, 1 to 1000. That is basically for all 1000 values. After that, plot 900, 1 to 1000. That is after thinning, after burning period. All right. And then I find out the histogram mean and variance of my last 100 values. All right. So whatever the mean I will get here, that will basically my estimated values of theta. That will be my estimated values of theta. Right. So here again we have the different questions here. So you can try these questions. Okay, question 1, 2, you can try. And after that, we have one thing that is important before introduce talking about other things, I want to talk about that one. Uh, Central limit theorem of Bayesian. I will talk about them later. Yeah, Bayesian central limit theorem that I want to talk about. So, what is this theorem? Is basically it says that suppose that x1, x2, xn follows the fx given theta. All right, that is x1, x2, xn is your random sample that follows any density fx theta with parameter theta, and theta where theta is the p-dimensional, means you have here you have theta 1, theta 2 up to theta p parameters. Okay, theta 1, theta 2, theta p parameters. P parameters you have in your density function, because in your density function you can have the multiple parameters, right? Correct. So, and the prior on theta is g theta. Okay, means theta I follows the g theta I prior distribution. The prior of g theta could be improper. Okay, the prior of theta means g theta I. This g theta I may be improper, but the we assume that the posterior is proper. Okay, means even you have the improper prior or proper prior, whatever the type of prior you have, after, even though you have the posterior is the proper prior, proper posterior distribution, means if you will find out the theta given x curve integral over the range of theta, that should be 1 if you have this form, and that is more exists, then as n tends to infinity, posterior of theta given x curve will follows the multivariate normal distribution with theta m and Hessian matrix, that is your H inverse theta m, where theta m is the posterior mode. Okay, basically what it says that what is the application of this one. If I want to show you with the research paper, did I upload this research? Did I upload these things here? No, give me a second. Uh, yeah, are you seeing this flow, this posterior density? Are you seeing this plot here? That is the basically following the Bayesian central limit theorem. What it means that basically what I did for each parameter. Okay, I have here how many parameters? For 12 parameters I am having here. So for all 12 parameters, I run the Metropolis algorithm or whatever the uh, MCMC chain or whatever the methods I used. I find out the chain of the parameters. Okay, I generated the chain of the parameters. What I am doing here basically, I am generating a chain. I am generating the numbers. 5,000 observation I generated, na? I generated 5,000 observation, right or not? In this Metropolis algorithm. So similarly, I find out the posterior estimate. Okay, I find out the posterior estimate of my theta here, and after that, the that one, the theta. Here theta is basically theta 1, theta 2, theta p. That will follows the multivariate normal distribution. Means that when I am going to generate, suppose for theta 1, when I am going to estimate, so in the approximation method, if you just see either Gibbs sampler or Metropolis algorithm, or you will see in the importance sampling or accept reject or Metropolis testing algorithm, in all methods, if you just see, we are generating a chain of theta 1, suppose theta 1 1, theta 1 2, up to theta 1 n, that we were doing in these all these methods, right or not? Yes or no? That this is the thing we are doing, right? all these methods. So it says that if I'm going to plot them, all these observations, it will follows the normal distribution. So if you just see in this figure, you will find all the plots are having the normal density, yes or no? So for large M, so what I did, I run these my code 100,000 times. Okay. So 100,000 times means n is 100,000, right? N is 100,000, right? So that means it tends to infinity. It is enough large. So it says that then when n tends to infinity, posterior of the theta means this n, theta 1, theta 2 are 100,000 observations that I am having. That will follows the multivariate normal distribution. Means if you just see the graph, it is basically multivariate normal distribution, right? So that is your Bayesian central limit theorem. So when you are going to run Metropolis algorithm, or you are going to run either gift sampler, or you are going to run either accept reject or Metropolis Hastings or importance sampling, in the last, if you are not getting these plots of your generated values like this, all right, of your estimated values of theta, if you are not getting this plot, that means there is some problem in your estimation or in the convergence. Okay, there is a problem in the convergence of your estimated value. It is not converged properly. Okay, when you are saying it is not converged properly, what is the meaning of this one? It is the how you will check that one. So for that one, what we need to do? For that one, first of all, the issue that we will say it as the issue in the chain efficiency. This term is called as the issue in the chain efficiency when using Markov chain algorithm to simulate the posterior density or the target distribution. We are concerned with the with regard to how well a chain runs. Some issues related to these problems are as follows. The burning in the sampler means when you are going to run this MCMC chain, you are going to run it again and again. So whatever the values it is generating the estimated values of your theta i's in the proper manner or not. How you will check it? So in that one, the key issue in the successful implementation of the MH or any other MCMC sampler is the number of run until the chain approaches to the stationarity. Okay, the length of the burn-in period. All right. Do you understand the stationarity? Do you understand the meaning of the stationarity? You studied the stochastic process, right? So tell me what is the stationarity? Stationary state. Okay. Any one of you went to the food corner here or any restaurant? Have you ever visited to any restaurant? Right? So when you visit to the restaurant, suppose the opening time of the restaurant is 8 a.m., right? And closing time is suppose 10 p.m. and lunch time is 1 to 2 p.m. So in which manner customer will arrive to the hotel or the restaurant? And this is the on y-axis you have the number of customers. How the in which manner customers arrive? In the 8 a.m. this is the breakfast time, right? 8 to 10. So the number of patients will be very high. So in number of patients, I'm saying number of customers is very high in the restaurant. Yes or no? right? After 10 o'clock, the number of customers will directly dip. They will not, there will be rarely you will get the customers in the restaurant after 10 a.m. up to 12. It will be very low and somehow constant. And in the lunchtime, what will happen? Again, it will be peak up to 1 to 2. And then after that, it will again goes down and you have the number of customers constant, and the dinner time, that is around 8 p.m. Okay, say it 8 p.m. here. 8 to 10 it will be high, and then it is closing time. It will look like that. That should be the graph of your of any restaurant, customer arriving at any restaurant. Yes or no? In the ideal situation. Yes or no? So here if you just see, you have the zigzag pattern here. Suddenly peak and suddenly you will see the downfall, right? So at that time, it is not stationary because you have the zigzag pattern. If the customer arrived in a similar manner across the time during the entire interval between closing to between opening to closing time, it is almost similar. Okay, it will call as the stationary state. Otherwise, it is non-stationary. So if you just see in the similar manner, if you are estimating the parameters here, okay, if some values are very high, then some values are very low, then some value again very high, some values again very low, and some value again very high. So whatever the estimated value you will get for the theta, the mean value, mean of theta, will be accurate or not, if it will follow this pattern. When you will run the chain, estimated chain, means MCMC chain, under any method that we studied till now, if you will get this type of chain, will your would your estimated values will be trustworthy or not? Your estimated value will be trustworthy or not? Not at all. But if you will get the values like this, almost stationary, all the values, generated value are close to each other, will it will be trustworthy or not? It will be trustworthy, right? So the stage reach the stationary state is very important. So how you will do that? So for that one, in that one, in the practice, so stationary state, the burn-in period is very important. So in the practice, 1,000 to 5,000 elements are thrown out, then one of the various convergence tests is used to assess whether the stationary has been reached or not. So a poor choice of the starting values or the proposal distribution can greatly increase the required burning time. Means whatever the proposal distribution that you are assuming. So in this one, in this previous example that I just discussed here, this one, here I assumed, in this one, I assumed that my theta star, I assumed from the uniform instead of the normal. Earlier I was assuming normal for the generalized Lindley, but here I assumed uniform. So because I assumed uniform, so it was easier to reach to the stationary state. Otherwise, if I assume normal distribution at that time, what will happen? I will get the values between minus infinity to infinity. But what is the value I can take here? 0 to 1. So what is the suitable proposal distribution for me here? Uniform only, right? So that's why I choose uniform. So That is the one condition here. Okay. So proposal distribution. After that, thus the main emphasis in the any MCMC sampler is the choice of the optimal starting point and the proposal distribution. One suggestion for the starting value is to start the chain as the close to the center of the distribution as possible. For example, taking the value close to the distribution mode. All right. After that, mixing. This is basically, this graph is called as the mixing. A chain is said to be poorly mixing if it is stayed in a small region for parameter space and for long period of the time as opposed to a well mixing stage. Not seems to happily explore the whole space. A poorly mixing chain can arise because of the targeted distribution is multimodal and our choice of the starting value is close to the one mode. All right. So two approaches have been suggested for the situation where the targeted distribution may have the multiple peaks. All right. Most straightforward is used multiple highly disparate initial values to start the several difference changes. All right. Another choice is used to simulate the nulling on the single chain. It means what you need to do here. Here, in the burn-in sampler, what you need to do when you have this type of situation, okay, you have the zigzag pattern. At that time, you are going to burn in some observation from the starting. Some observation you are going to burn in, and after that you will start. And then the mixing problem is there. Basically, how well your chain is starting. For that one, we have the graph here. If you just see here, this one. This is called the trace plot. So if you just see here, you will not find the zigzag pattern. Are you finding any zigzag pattern in this graph that I showed you earlier? It is well mixed, right? Because I started with the proper initial guess. Okay. If you are going to start your code or your program with a very weak or any random initial guess, your chain will not mix well. So if your model is a see here, what was the thing in the R code? We had the only one unknown value in this code. What we are generating in this code? We were generating only Z. Only one value was unknown. Yes or no? Right. So that's why it was easy to converge and it was easy to mixing well. But if your model is multimodal, means you have the multiple unknown values. Means if you have the theta 1, theta 2, theta p parameters, 10 or 12 parameters are there. Like here, I have the 12 parameters in this model. So I need the 12 initial values here. For each parameter, I need the single initial value. If those initial values are not proper, so at that time it can create the problem to mix all the to generate this kind of trace plot that where the estimated values of theta 1, theta 2, theta p are well mixed. So that problem arises at that time when you don't have the initial guess of the parameters to estimate the parameters for the given model. I would like to tell you here one thing. To get the initial get is the more tough in compare to estimate the values from the MCMC. Find out the initial guess is much tougher in compare to estimate the value. When I just use this one, I estimate these values. Sometimes it takes 1 month, sometimes it takes 1 day, and sometimes it takes more than 2 or 3 months for me to find out the initial guess to start the estimate. Before starting the estimates, I need the initial value. To find out the initial value, okay, what should be my initial value? Sometimes I take 2.5 months. When I was writing my first research paper in my PhD, it took me around 6 or 7 months to get the first initial gas for this, for the MCMC code. When you have the more number of parameters, if you have 2 or 3 parameters, then it is not difficult. But if you just see, I have the 12 parameters. I don't think you have seen the 12 parameters till this date, till now, in any distribution or anywhere, right? So it takes more time, most of the time. 12 means 6 or 7 months is a very difficult, very long time to get the initial gas. And when I'm saying that 6 months, I was sitting for 8 hours every single day without any break. 8 hours every day means 6 months, all 24/7, all 7 days without break, 8 hours continuously. Then I got my first initial gas. All right. After that, I get the idea. Okay, for which distribution where I will get the initial gas. So now it takes less time. Now it takes 5 or 10 days for me to find out the initial gas when I'm doing the data analysis, real data analysis for the any given model like this, right? So that is the mix. For the mixing well, initial gas is very important. Most of the people don't follow that thing. Even they don't know this concept of the initial gas, finding the initial gas or finding the well mixing. All right. So choosing the proposal distribution, since that is the thing that I already told you, that since the Metropolis sampler works with the any symmetric distribution, while MH algorithm is even more general, the problem is the choice of the suitable proposal distribution. There are two general approaches: random walk and independent chain sampling. All right. Under the sampler using the proposal distribution using the random walk chain, the new y is equals to the current values of x plus random value of z. That is the one way to find out your proposal distribution. All right. After that, the convergence diagnostic of the Markov chain. So if you have this type of graph, zigzag pattern, you don't know. Here you can claim that it is, I am able to see that my results are not trustworthy. But if I am getting the graph like this, so it look like the stationary somehow in compared to all these two or three, it look like a stationary. Yes or no? It look like a stationary third graph or not? Somehow it is looking like a stationary, but it is properly reached to the stationary state or not, that we cannot say from the graphical representation. So for that one, we use some test here. Okay, for the convergence, first of all, first is the autocorrelation and the sample size inflation. All right. So first of all, we find out the autocorrelation. What is the autocorrelation? Is basically covariance between theta t comma theta t plus k divided by variance of theta t. Right. What is it basically? This is the autocorrelation formula. What we are going to do basically, why we are taking theta t plus k, we are not taking theta t plus 1. So here two things are there. First, we are going to, if I am generating a chain, theta 1, theta 2, up to, suppose theta k plus 1, or you can say, yes, and up to theta. I have these observations. That is the chain that I get after the applying my MCMC algorithm. So in that one, I am going to remove first k observations. That will call as the burn-in. That is called as the burn-in period. I told you earlier this one, right? After that, I have the observation theta k plus 1, theta k plus 2, up to theta n. This is my another vector, my remaining vector. After that, what I will do, I will take the leg of uh, say n1, means I will take value theta k plus 1. After that, I will not take the theta k plus 2. I will take theta k plus n1 plus 1. Then I will take theta k plus 2 n1 plus 1, theta k plus n2, oh sorry, 3 n1 plus 1, and so on up to theta n. I will take the values in that one. So I will remove some values. All right. So now what I need to do, I need to find out the autocorrelation between these two observations. So I need to find out the autocorrelation between theta k plus 1 and theta k plus n1 plus 1. That is my first autocorrelation. After that, I need to find out the autocorrelation between rho theta k plus n1 plus 1 and theta k plus 2n1 plus 1. That's how I need to find out the autocorrelation between the values. Okay, so I will find out this autocorrelation. If this autocorrelation that I am finding, it is negligible, my chain is mixing well, my chain is reaching to the stationary state, whatever these estimates are reaching to the estimate, that one. After that, I can find out the mean of this one. I can find out the mean of this observations. That will be my estimated value if variance is, autocorrelation is negligible. If you just see here, you will find the negligible autocorrelation. All right. You are finding the negligible autocorrelation here. Right. I showed you earlier how to find out the autocorrelation. For that one, command is ACF in R. Right. Command was ACF. ACF of Z new. Right. This is your ACF. This is negligible. Right. First thing is that one. After that, autocorrelation process is basically coming from the autoregressive process. AR1 from your time series. Did you study the time series? Okay, so I will not go in that one. Otherwise, it is basically comes from the autocorrelation formula comes from the autoregressive method in from the time series. Okay, where we generate the where present observations depends on the just past observation. Do you understand the concept of the time series? Do you understand the concept of the time series? What is the how you forecast the future value? Your current value depends on your previous values, right? If I know the stock price of the past 10 days of any particular stock, so I can forecast the tomorrow's stock price of particular share or not, right? So in the same manner, we are checking this one autocorrelation. All right. So after that, we have some test for the convergence. So there are several tests are there. In that one, we have first one is the Gawake test, and then we have the Referee-Lewis test. So how we apply the test? We don't apply the test on all these observations, theta 1, theta 2 up to theta n. We apply the test on these observations after burning and after taking the leg. Okay, on these observations. So Glavin-Rubin test was given by Glavin-Rubin in 1992. All right. So what is that one? Oh, sorry, Gawake test. is 1992. So what we are going to do in the test, we are going to split the sample after removing a burn-in period or lag into two plots, first 10% and last 50%. Means what we are going to do, we have these observations right now. We have these observations, theta k plus 1, theta k plus n1 plus 1, and up to theta n, these observations. So what I will do, I will split this entire sample into two parts. I will take 10% observation of first 10% observation and last 50% observation I will consider. Okay. After that, if the chain is at the stationary means of the two samples is equals, means if chain is going to reach to the stationary state, so in that one, if chain is reaching to the stationary state, so if I'm going to take this 10% sample and this 50% sample, so the mean of both parts should be equal or not? The average of both part 10% and 50%, this initial 10%, the last 50% should be same or not? It should be same. If it is going to stationary means if they have the same distribution. So at that time, we will apply the Z test to compare two sample two sample test. Okay, two sample Z test we will apply and we check that whether they have the equal mean or not. If they have the equal mean, we will say the chain reach to the convergence state or can converge properly and reach to the stationary state. Otherwise, chain is not converged properly if the mean they have the different mean. All right. So that is the Gawake test. And similarly, we have the Refre-Lewis test. In that one, what we will do, we apply the quantile. Okay. A more informative approach is the Refre-Lewis test. But in the Refre-Lewis test, what is the problem? We need the more observation. Here, you don't have any restriction on the observation. Okay, but here in the Refre-Lewis test, you have the restriction that when you are going to apply the Refre-Lewis test, the size of this sample after thinning and that one taking the leg, the sample size should be at least 3700. You should have at least 3700 observation after burn-in period and after taking the leg. But in that one, in the in the Gawake test, you don't need any this kind of restriction. Okay. So after that, what you will do, you will take the 2.5% and the 97.5% to give a 95% confidence interval. Quantile function you are going to take and the accuracy of the quantile and the power 1 minus beta to achieve this accuracy of the specified quantile with these three parameters set. Refre-Lewis test break the chain into a 1-0 sequence if theta t is less than equals to q. All right, that is quantile, take 1 otherwise 0. This generate a two-state Markov chain and the Refre-Lewis test use the sequence to estimate the transition probability with the probability in hand. One can then estimate the number of additional burn-in if any required. All right, so what we are going to do here, okay, this is the gift sampler that we have discussed already, right? So these are the two tests, Gawake test and Refre-Lewis test. In the Refre-Lewis test, we are going to use the quantile function, okay, and in Gawake test, we use the Z test. Here, I think I have used another test also, if I am not wrong. Yeah, this is Helberg-Welch test is there. Okay, Helberg-Welch test for the convergence. That is the another test here. Okay, here what it will provide you. It again the test use the same kind of testing. If I just show you, I think I have written where did I write? Did I write? Uh, yes. So to check the convergence of the MCMC chain, we apply the Hilbert-Welch test that was given in 1981. All right. So the Kramer-von Mises statistics is used. So maybe you don't know. You know the MLE to find out the estimate of the parameter, right? Did you know that one least square method to find out the estimates of the parameter? So similarly of the least square and the MLE, we have the one more method to find out the estimates that is called the Kramer-von Mises statistics. Okay, that is the method to find out the estimates of the parameters. So we use this method to check the convergence, the test, and we equate the assumption that the selected values from a stationary distribution. Okay, so the test is performed in the steps, starting with entire chain and working down with the first 10%, 20% until the null hypothesis is proved or 50% of the chain has been eliminated. What we will do, we will take the first, we will take 10% observation and then we will check whether they are going to reach to the stationary state or not. After that, we will take 20% and we will check whether they are going to reach to the stationary state or not. Up to like that, we will take up to the 50% observations and then we check it is reached to the stationary state or not. All right. So in that one, it always provide the p-value. All right. If the p-value of the test is greater than 0.05, you say that your chain is reaching to the stationary state. Otherwise, chain is not converged completely till now. Okay. But if it is greater than 0.05, but it should be around 0.7 for the perfect convergence. Like that, if you just see here, I am having the value 0.167. It is converged, but not the perfect convergence I didn't get here. All right, so this is for second parameter, delta 1. So if I just see here, I am getting the plot that is showing the proper convergence, but not the exact one. But test is showing that what is the difference between the applying test and the graphical representation. Here it is showing the perfect mixing, yes or no, this graph showing perfect mixing as well as convergence. ACF is not there in this plot. ACF is not present and it is perfectly normally distributed from the Bayesian center limit theorem. But what is the test is saying? Test is saying that it is converged but not the perfect convergence because it is greater than 0.05 but not near to 1. It should be near to 1 to get the perfect convergence, right? That is your convergence test basically. Time's up or how? What is the time? Time's up. Okay. So we will stop here.